In order to examine more general cases, we will introduce the Maxwell stress tensor describing the interaction between an electrostatic field and a charged insulating material. Firstly, we consider a homogeneous liquid dielectric medium of relative permittivity εr. In electrostatic, the two Maxwell equations tell us that the divergence of the electric displacement field D in the medium is equal to the free charge density ρ, and the electrostatic field E is curl-free. In a linear dielectric, the displacement vector D is given by the vacuum permittivity ε0 times the relative permittivity εr of the dielectric, times the electric field strength E in the dielectric, where εr is constant due to the homogeneity of the medium. The product of ε0 and epsilon defines the absolute permittivity ε of the dielectric. If we insert this expression into the first Maxwell equation, then we can write the volume charge density ρ of free charges as the divergence of the product of the absolute permittivity ε and the electric field strength E. Since epsilon is a constant, it can be factored out, that is ρ is equal to epsilon times the divergence of the field strength E. Now we assume that the electrostatic force density F in the medium is given by the charge density ρ times the field strength E for dielectric fluids. By applying the expression obtained for ρ, the force density can be written as epsilon times the divergence of E, times E. In order to transform the right-hand side into a more convenient form, we use the vector identity for the tensor divergence of the tensor products of two arbitrary vector fields, let us say V and W, stating that the divergence is equal to the divergence of the vector V times the vector W, plus the directional derivative of the vector W with respect to the vector V. If both the vectors are equal to the electric field strength E, then the divergence of the tensor product of E with itself is given by the divergence of E times E, plus the directional derivative of E with respect to itself. Here the second term can also be written as nabla sub E, indicating that the derivative of the vector field E is taken in the direction of E. We also apply another vector identity for the gradient of the dot products of the vector fields V and W, stating that it is equal to the derivative of W in the direction of V, plus the derivative of V in the direction of W, plus the cross product of V with the curl of W, plus the cross product of W with the curl of V. For V and W equal E, this identity can be reduced to the equation stating that the gradient of E squared is given by 2 times the derivative of E in the direction of E, plus 2 times the cross product of E and the curl of E. The second term in the right-hand side vanishes due to the fact that the electrostatic field E is curl-free, as stated in the second Maxwell equation. If we combine the two identities applied for the field strength E by eliminating its directional derivative with respect to itself, then we can write the divergence of E times E as the divergence of the tensor product of E with itself, minus the gradient of 1/2 times E squared. This result can be substituted into the equation for the force density F, where we can factor out the nabla operator and write F as the absolute dielectric constant epsilon times the divergence of the difference between the tensor product of the field strength E with itself, and 1/2 times the square of the magnitude of the field strength E times the unit tensor I. Now we introduce the Maxwell stress tensor T of the electrostatic field E in a homogeneous dielectric medium of absolute permittivity epsilon in the form epsilon times the difference between the tensor product of the field strength E with itself, and 1/2 times the square of the magnitude of the field strength E times the unit tensor I. This quantity is a tensor of rank 2, which can be represented by a matrix with the tensor components in a given coordinate system. If we attach a Cartesian coordinate system to the insulating material of dielectric constant epsilon placed in the electric field E, then the components ij of the stress tensor T are given by epsilon times the difference between the I component of the vector E times the j component of the vector E, and 1/2 times E squared times the Kronecker delta sub ij, where the indices I and j denote the Cartesian coordinates x, y, and z. As a result, we can express the electrostatic force density F exerted on a dielectric medium by an electrostatic field as the divergence of the Maxwell stress tensor of the field in that medium. Then the electrostatic force F acting on the insulating material given by the volume integral of the force density over the volume V occupied by the material, is equal to the volume integral of the divergence of the Maxwell stress tensor of the field in the material. By applying the divergence theorem, the electrostatic force F can be written as the surface integral of the stress tensor T over the boundary surface S of the volume V. Now we provide the physical interpretation of the Maxwell stress tensor. Firstly, we note that since the relative permittivity of a vacuum is exactly 1, the absolute dielectric constant epsilon appearing in the definition of the stress tensor is equal to the dielectric constant epsilon not in a vacuum. In many cases this tensor is defined by applying vacuum permittivity, that is for an electrostatic field in a vacuum. If we expand the stress tensor in a Cartesian coordinate system, then we can represent its components the following matrix. By definition, the Maxwell stress tensor is symmetric and represented by a symmetric matrix. We already saw that the surface integral of the stress tensor of an electrostatic field over the surface of a body in the field gives the total electrostatic force acting on the body. This fact indicates that the components of the tensor represent a force per unit area exerted by the electrostatic field. Indeed, we can consider the SI unit of the absolute dielectric constant that is equal to the unit of the vacuum permittivity epsilon naught, which is given by farad per meter, or Newton per volt squared. Since the SI unit of the electric field strength E is equal to volt per meter, the matrix elements show that the SI unit of the components of the stress tensor is given by the product of Newton per volt squared and the square of volt per meter. This expression gives Newton per square meter, indicating that the components of the Maxwell stress tensor represent either pressure or shear stresses exerted on the body by the electric field. If we examine the elements of the matrix representing the tensor, we can see that its diagonal components describe either the pressure or the pulling tension exerted on planes perpendicular to the respective direction. We can talk about pressure or tension depending on the sign of the difference between the two terms in the diagonal components. If the first term describing the longitudinal tension of the electric field is less than the second term representing the isotropic pressure, that is, the component is negative, then we can talk about the pressure exerted on the planes by the electric field. If the second term is less than the first one, that is, the diagonal component is positive, then it describes the tension produced by the field. For example, let us consider the XX component of the stress tensor given by the absolute permittivity epsilon, times the difference between the square of the X component of the electric field strength E and 1/2, times the square of the magnitude of the vector E. This component describes the force per unit area in the X direction acting on a planar surface element perpendicular to the X-axis. In the figure, this component is represented by the blue arrow pointing outward from the blue face of the rectangular volume element with faces parallel with the Cartesian coordinate axes. The blue arrow representing the positive component T sub XX is interpreted as the pulling tension exerted in the X direction on the blue face of the volume element perpendicular to the X direction. If the component T sub XX is negative, then the blue arrow points inward and represents the pressure exerted on the blue face of the volume element in the X direction. The same interpretation holds for the other two diagonal components T sub YY and T sub ZZ, indicated by the directions and the orientations of the yellow and red arrows pointing outward from the yellow and red faces of the volume element. The off-diagonal components of the Maxwell stress tensor represent the shear stresses on planes that are parallel with the respective direction. For example, the component T sub XY of the stress tensor is given by the absolute permittivity epsilon times the product of the X and Y components of the electric field strength E. This component is represented by the yellow arrow lying in the plane of the blue face of the volume element and pointing in the Y direction. This quantity is interpreted as the shear stress acting on the blue area element perpendicular to the X-axis acting in the direction of the Y-axis. Similarly, the component T sub XZ describes the shear stress exerted on the blue area element in the Z direction, indicated by the red arrow. The same interpretation can be made for the other off-diagonal components represented by the arrows lying in the yellow and red faces of the volume element. As in the case of the dielectric tensor or the susceptibility tensor of insulating materials, the Maxwell stress tensor T of rank 2 can also be interpreted as a linear map between vector spaces. That is, it maps an arbitrary vector v into another vector which is given by the contraction of the tensor T and the vector v. The later can simply be computed by a matrix vector multiplication of the matrix of the tensor T and the column vector of the vector v expanded in some coordinate basis. If the vector v is a unit vector, its contraction with the stress tensor T gives the traction produced by the electric field in the direction of the unit vector. Since the stress tensor is a tensor of rank 2, it can also be interpreted as a multilinear map from the Cartesian product of two vectors to scalars. The tensor T can be evaluated at two arbitrary vectors v and w, which is simply the composition of the contraction of the tensor T with the vector w, and the dot product of the result of the contraction and the vector v. This operation has also a simple representation when the vectors and the tensor are expanded in some coordinate basis. Then the result of the matrix vector multiplication of T and W gives a column vector that can be contracted by the row vector of the components of V. We also saw that the Maxwell stress tensor is symmetric, that is, if we exchange the vectors V and W then we obtain the same result. This symmetry has a deep physical meaning as we will see when we evaluate this second-rank tensor at unit vectors pointing into arbitrary directions. If we evaluate the stress tensor T at a normal vector n to an area element, then we obtain the normal electrostatic stress or traction acting on that area element. Its explicit term is given by the absolute permittivity epsilon of the medium surrounding the area element, times the difference between the square of the normal component of the electric field strength E to the area element, and 1 over 2, times the square of the field strength E. Again, by expanding the parentheses we obtain two terms describing the longitudinal tension and the isotropic pressure exerted on the area element by the field. We can also evaluate the Maxwell stress tensor at two unit vectors n and m, which gives the projection of the electrostatic traction in a given direction. This is equal to epsilon times the product of the components of the field strength E in the directions of the vectors n and m, describing the traction in the direction of the unit vector m across the area element oriented in the direction of the unit vector n. If we consider two area elements with the normal vectors n and m, then the symmetry of the tensor just means that the traction or the shear force acting in the direction of the normal to the first area element across a second surface element is equal to the shear force acting in the direction of the normal to the second area element across the first area element. This force balance prevents area elements from spontaneously spinning, that is, electrostatic fields do not exert a net internal torque density on infinitesimal volume elements. Consequently, the symmetry of the stress tensor guarantees the conservation of angular momentum within electrostatic fields and ensures that the field do not exert a net self-torque on a closed system. As an illustration of the application of the Maxwell stress tensor in electrostatics, we revisit the problem of a homogeneous dielectric sphere immersed in a liquid dielectric, where the sphere is charged and the whole system is polarized by a uniform electric field. Here the uniformly charged sphere of radius R has the charge q, and the external electric field E0 points in the z direction. Epsilon 1 and epsilon 2 denote the absolute permittivities of the liquid dielectric and the dielectric sphere, respectively. At a given point P outside the sphere described by the position vector or pointing from the center of the sphere to the point P, we can express the total electric field E as the superposition of three different fields. The Coulomb field EQ due to the electric charge Q of the dielectric sphere, the induced dipole field E' of the polarized sphere, and the external field E0 applied on the liquid dielectric. In order to describe these fields we use a spherical coordinate system adapted to the position of the dielectric sphere and the direction of the external electric field, that is with the origin at the center of the sphere and the polar axis pointing in the z direction. Then the coordinate components of the physical fields in the problem have no azimuthal dependence, and the unit vector pointing in the z direction can be decomposed as the cosine of the polar angle theta times the unit vector ER pointing in the radial direction, minus sine theta times the unit vector E theta pointing in the polar direction. As a result, the magnitude of the Coulomb field EQ is simply equal to 1 over 4 pi times the absolute permittivity epsilon 1 of the dielectric fluid, times the charge q of the sphere over the square of the distance r between the center of the sphere and the point P. The unit vector ER determines the radial direction of the field pointing outward. For the sake of brevity we denote the magnitude of the Coulomb field by E sub q1, which is a function of the distance r. The index 1 indicates that the expression of the magnitude contains the dielectric constant epsilon 1. For the induced field E' around the small polarized sphere we can apply the electric dipole approximation and assume that this field is produced by an induced dipole of electric dipole moment P. We already derived the formula describing a dipole field in a vacuum. Then the field strength E' of such a field in a dielectric medium at the point P determined by the position vector R can be written as 1 over 4 pi times the absolute permittivity epsilon 1 of the medium, times the difference between 3 times the dot product of the vectors P and R times R, and R squared times the vector P, over R to the 5th power. Since the dipole moment P of the uniformly polarized sphere points in the direction of the external electric field E0, that is in the z direction, it can be expressed in terms of the radial unit vector ER and the polar unit vector E theta. If we substitute this decomposition into the numerator of the fraction in the expression describing E', and write the dot product of the vectors P and R as the product of their magnitudes times cosine theta, then the numerator can be written as the difference between 2 times P times R squared times cosine theta times the unit vector ER, and R squared times P times sine theta times the unit vector E theta. By inserting this expression into the right-hand side of the equation describing the polarization field, it can be expressed as the dipole moment P over 4 pi times the permittivity epsilon 1 times the distance R cubed, times the sum of 2 times cosine theta times the unit vector ER and sine theta times the unit vector E theta. Here we also introduce the shorthand notation EP for the multiplication factor P over 4 pi times epsilon 1 times R cubed. The last electric field that has a contribution to the field outside the sphere is the external field E0 written as its magnitude E0 times the unit vector pointing in the z direction, where we decompose the unit vector in the radial and polar directions as well. Now we can write the radial and polar components of the electric field outside the charged and polarized dielectric sphere as follows. Its component in the radial direction is equal to E sub q1 plus 2 times EP times cosine theta plus E naught cosine theta, whereas its polar component is given by EP times sine theta minus E naught times sine theta. The electric field inside the sphere is the superposition of two fields, the Coulomb field due to the charge Q and the cavity field EC due to the polarized dielectric fluid surrounding the sphere modified by the polarization field in the dielectric sphere. Since we assume that the sphere has a uniform charge distribution, the magnitude of the electric field EQ at any point within the sphere can be written as 1 over 4 pi times the absolute dielectric constant epsilon 2 of the sphere, times the charge Q over the cube of the radius capital R, times the distance r between the point and the center of the sphere. The direction of the spherically symmetric field is given by the radial unit vector ER. Here we also introduce the notation E sub q2 for the magnitude of the field. The cavity field EC modified by the polarized sphere has the same direction as the external electric field polarizing the whole system, and it is given by the magnitude of EC times the unit vector EZ pointing in the z direction. The later can be decomposed into the radial and polar directions as well. As a result, the radial component of the internal electric field is equal to E sub q2 plus EC times cosine theta, whereas its polar component is given by negative EC times sine theta. In the next step we apply the boundary conditions of the quantities describing the electric field inside and outside the sphere. We already studied the behavior of the field strength and the displacement field across a boundary interface between two dissimilar dielectrics. We found that the tangential component of the field strength E is continuous across the interface, that is, the tangential component of the field strength outside the sphere is equal to the tangential component of the field strength inside the sphere over the boundary surface of the sphere. We also established that the normal component of the displacement field D is discontinuous across the interface, that is, the difference between the normal component of the displacement field outside the sphere and the normal component of the displacement field inside the sphere is equal to the surface charge density sigma of the free charges over the boundary surface of the sphere. The boundary condition for the normal component of the field is represented by the condition for the polar components of the fields outside and inside the sphere, as the azimuthal component of the field vanishes due to its symmetry about the z-axis passing through the center of the sphere. That is, the polar components of the electric field strengths outside and inside the sphere must be equal to each other at the boundary interface at the radius capital R of the sphere. If we substitute the expressions obtained for the polar components of the electric field strengths outside and inside the sphere into this condition, then we can write the equation stating that EP evaluated at capital R times sine theta minus E naught times sine theta is equal to negative EC times sine theta. This condition must hold for an arbitrary polar angle. Therefore, we reduce this equation to the condition stating that EP evaluated at capital R minus E naught is equal to negative EC. We follow the same procedure for the boundary condition describing the jump of the displacement field across the interface. Because the displacement vector D is given by the absolute dielectric constant of the given medium times the field strength E, the condition for the normal component of the displacement field across the interface at the boundary of the sphere states that the difference between epsilon 1 times the radial component of the electric field strength E outside the sphere and the epsilon 2 times the radial component of the electric field strength E inside the sphere is equal to the surface density sigma of the free charges over the interface. We assume that the free charge Q is distributed uniformly throughout a volume of the sphere, which drops to 0 over the infinitely thin shell representing the boundary interface. That is, the surface charge density sigma of free charges vanishes over the interface. Now we use the expressions obtained for the radial components of the electric field strength outside and inside the sphere evaluated at the radius capital R, and substitute them into the equation of the boundary condition. We also insert the definitions of the shorthand notations E sub q1, E sub q2, and EP into this equation, where each of them is evaluated at the radius capital R. If we expand the parentheses, we can see that the terms containing the charge Q cancel out each other and the equation can be reduced to the form, stating that the quantity of P over 4 pi times capital R cubed plus epsilon 1 times E naught minus epsilon 2 times EC multiplied by cosine theta, is equal to 0. This equation must hold true across all angles theta around the sphere, that is, the quantity in the parentheses must vanish. We also substitute the definition of E sub q1 into the first boundary condition and we obtain two equations that can be used to eliminate the variable EC by multiplying the second one by epsilon 2 and adding the result to the first equation. Then we can express East P evaluated at capital R, that is P over 4 pi times epsilon 1 times capital R cubed, as the difference between the dielectric constants epsilon 2 and epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times the magnitude of the external field E naught. Now we can evaluate the radial and polar components of the electric field outside the sphere over the boundary interface between the dielectric fluid and the sphere, by inserting the expression of EP evaluated at the radius R into the component equations. For the radial component we obtain E sub q1 evaluated at R, plus 2 times the ratio of epsilon 2 minus epsilon 1 to epsilon 2 plus 2 times epsilon 1, times E naught times cosine theta, plus E naught times cosine theta. The second and the third terms in the right-hand side can be reduced to the term 3 times epsilon 2 over epsilon 2 plus 2 times epsilon 1, times E naught times cosine theta. Here we introduce the notation AN for E sub q1, and the notation B for 3 times epsilon 2 over epsilon 2 plus 2 times epsilon 1, times E naught. Then the radial component of the electric field strength E evaluated at the radius R can be written as A plus B times cosine theta. Similarly, for the polar component of the field strength E evaluated at R we obtain the ratio of epsilon 2 minus epsilon 1 to epsilon 2 plus 2 times epsilon 1, times E naught times sine theta, minus E naught times sine theta. The right-hand side can be written as negative 3 times epsilon 1 over epsilon 2 plus 2 times epsilon 1, times E naught times sine theta, where we introduce the notation C for negative 3 times epsilon 1 over epsilon 2 plus 2 times epsilon 1, times E naught. Then the polar component of the field strength E at the radius R can be expressed by C times sine theta. Now we are able to determine the Maxwell stress tensor of the net electric field on the boundary interface between the dielectric sphere and the liquid dielectric surrounding the sphere by evaluating the field over the interface and the fluid side. Outside the sphere the stress tensor T is defined by the absolute permittivity epsilon 1 of the liquid dielectric, times the difference between the tensor product of the electric field strength E outside the sphere with itself, and 1 over 2 times the square of the magnitude of the field strength E times the unit tensor I. For the sake of brevity we drop the subscript of the field strength E indicating that it describes the field outside the sphere. We will determine the components of the stress tensor in the spherical coordinate system that are relevant to the calculation of the force exerted on the sphere by the electric field. Firstly, we evaluate the stress tensor T in both of its arguments at the radial unit vector, which gives epsilon 1 times the difference between the dot product of the field strength E with the radial unit vector ER times the same dot product, and 1 over 2 times E squared times the dot product of the radial unit vector ER with itself. This gives epsilon 1 times the difference between the square of the radial component of the field strength E, minus 1 over 2 times epsilon 1 times the square of the magnitude of the field strength E. Since the azimuthal component of the electric field E vanishes due to its symmetry about the z-axis, the square of its magnitude is equal to the sum of the square of its radial component and the square of its polar component. As a result, we obtain 1 over 2 times epsilon 1, times the difference between ER squared and E theta squared. Now we can substitute the expressions obtained for the radial and polar components of the field strength E outside the sphere into the right-hand side of this equation. By expanding the terms in the parentheses we can write the pure radial component of the Maxwell stress tensor T as 1 over 2, times epsilon 1, times the quantity of A squared plus 2 times A times B times cosine theta, plus B squared times the square of cosine theta, minus C squared times the square of sine theta. We also determine the mixed component theta R of the stress tensor T by evaluating it at the polar and radial unit vectors, which gives epsilon 1, times the difference between the dot product of the field strength E with the polar unit vector E theta times the dot product of the field strength E with the radial unit vector ER, and 1 over 2 times the square of the magnitude of the field strength E times the dot product of the polar and radial unit vectors E theta and ER. Since the basis vectors of the spherical coordinate system are mutually orthogonal, the second term in the bracket vanishes and we obtain epsilon 1 times the product of the radial and the polar components of the field strength E. If we substitute the expressions obtained for the radial and polar components of the field strength E into the right-hand side of the equation, then the theta R component of the stress tensor T can be written as epsilon 1 times the sum of A times C times sine theta and B times C times cosine theta times sine theta. These tensor components can be used to evaluate the stress tensor at the unit vector Ez pointing in the direction of the external electric field E0 and at the radial unit vector Er. We already decomposed the unit vector Ez as the difference between cosine theta times the radial unit vector Er and sine theta times the polar unit vector E theta. If we insert this decomposition into the stress tensor T evaluated at the vectors Ez and Er, we can split it into the difference between the stress tensor T evaluated in its both arguments at the radial unit vector Er times cosine theta, and the stress tensor T evaluated at the polar unit vector E theta and the radial unit vector Er times sine theta. The expressions derived for the tensor components in the right-hand side can be substituted here, and we can express the stress tensor evaluated at the vector Ez and Er over the boundary interface between the liquid and the sphere in terms of the constants A, B, and C, and the polar angle theta. In the last step we determine the total force acting on the charged dielectric sphere submerged in the liquid dielectric under the influence of an external uniform electric field. We already established that the force F acting on a body in an electric field can be expressed by the surface integral of the Maxwell stress tensor T of the field over the boundary surface S of the body. In the case of a sphere, this surface integral can be written as the integral of the contraction of the tensor T with the radial unit vector Er pointing the normal to the surface of the sphere. Now the force exerted on the dielectric sphere can be decomposed in the z direction of the external electric field and its transversal component, where the later is cancelled due to the symmetry of the problem. Then it is enough to determine the z component of the force F given by the dot product of the force vector F and the unit vector Ez pointing in the z direction. If we substitute the surface integral into the force vector F, then we obtain a surface integral of the Maxwell stress tensor T evaluated at the unit vector Ez and the radial unit vector Er over the boundary surface S of the sphere. By inserting the expression that we derived for the stress tensor evaluated at the vectors Ez and Er into the right-hand side, we can split the surface integral into two terms. The first term is equal to 1 over 2 times epsilon 1, times the surface integral of the terms in the parentheses times cosine theta, where we have a squared plus 2 times a times b times cosine theta, plus b squared times the square of cosine theta, minus c squared times the square of sine theta in the parentheses. Similarly, the second term is given by negative epsilon 1 times the surface integral of the terms in the parentheses times sine theta, where we have a times c times sine theta, plus b times cosine theta times sine theta in the parentheses. Then we transform the surface integrals over the boundary surface S of the sphere of radius R into the integrals over the full solid angle by substituting the surface element ds with r squared times the infinitesimal solid angle d omega. Here we also factor the constants a, b, and c out of the integrals over the full solid angle. As a result, the integrands become purely trigonometric functions of the polar angle and the products of these trigonometric functions, which are integrated over the full solid angle. For cosine theta, the cube of cosine theta, and cosine theta times the square of sine theta, these integrals vanish. The only terms integrated over the full solid angle that give non-zero results are the integral of the square of cosine theta, which is equal to 4 pi over 3, and the integral of the square of sine theta, which is equal to 8 pi over 3. Then we can write the z component of the force F as 4 pi over 3, times epsilon 1 times r squared times a, times the difference between b and 2 times c. Now we substitute the definitions of the constants a, b, and c into the right-hand side of the equation, where a is given by 1 over 4 pi times epsilon 1, times q over the square of capital R, b is equal to 3 times epsilon 2 over the sum of epsilon 2 and 2 times epsilon 1, times e naught, and c is given by negative 3 times epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times e naught. If we simplify the result, the multiplication factor of the terms in the parentheses reduces to q, and the terms in the parentheses can be written as the sum of epsilon 2 and 2 times epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times e naught. This just gives q times e naught, and we have proven that for liquid dielectrics the resultant force F of the electrostatic and mechanical forces acting on the charged sphere surrounded by a dielectric medium is given by the charge q of the sphere times the external electric field E naught acting on the liquid and the sphere. As already stated, this result holds for any charged body of arbitrary shape. The phrase mechanical forces in this statement might be somewhat misleading, since the force F acting on the charged body has a purely electrostatic origin transmitted through the polarized liquid dielectric as a stress or pressure exerted on the charged and polarized dielectric sphere. The total force acting on the sphere immersed in the dielectric fluid also includes the forces due to hydrostatic pressure, gravity and buoyancy, that is the force F is given by the charge q times the field strength E naught, plus the mass m of the body times the gravitational acceleration g, minus the density ρ of the liquid times the volume v of the body times the gravitational acceleration g, or simply q times E naught plus the difference between the mass m and the density ρ times the volume v, times the gravitational acceleration g. We also note that when we consider the electric field EC inside the sphere we interpreted it as the cavity field produced by the polarized liquid dielectric surrounding the sphere, which is modified by the polarization field of the dielectric sphere. We saw that it can be written as negative EP evaluated at capital R, plus the external electric field E naught. Because we expressed EP evaluated at capital R as the difference between epsilon 2 and epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times E naught, the field EC can be written as 3 times epsilon 1 over the sum of epsilon 2 and 2 times epsilon 1, times E naught. But this is equal to the negative constant C, that is, the later represents the uniform electric field inside the sphere. We also see that the constant B has a similar form, and it in fact describes the electric field in the liquid layer immediately surrounding the sphere. We finish the presentation about the Maxwell stress tensor of an electrostatic field with the generalization of the electrostatic force density formula by introducing the so-called Korteweg-Helmholtz force density. As already shown, the electrostatic force density F acting on a body made of dielectric material under the influence of an electrostatic field is given by the free charge density ρF in the body, times the electric field strength E of the field. Here we use the subscript F for the volume density of free charges, while the letter ρ without any subscript will denote the density of the dielectric material. We also prove that the force density F can be expressed by the tensor divergence of the Maxwell stress tensor T defined by the absolute permittivity epsilon of the dielectric, times the difference between the tensor product of the field strength E with itself, and 1 over 2 times the square of the magnitude of the field strength E times the unit tensor I. However, we derive this expression by supposing that the dielectric material polarized in the electrostatic field is homogeneous and its permittivity is constant. It is not the case for an inhomogeneous dielectric medium where the permittivity of the material depends on the position r, that is, epsilon does not commute with the nabla operator. If we assume that the force density is given by the tensor divergence of the stress tensor and the form of the tensor is still the same for inhomogeneous insulating materials, then we need to generalize the formula for the force density for such cases. If we substitute the expression of the stress tensor into the divergence in the right-hand side of the force density formula, then the later can be split into two terms. The tensor divergence of the tensor product of epsilon times E, and negative 1 over 2 times the gradient of the product of epsilon and E squared. By expanding the bracket in the first term in the right-hand side, we write it as the directional derivative of epsilon in the direction of the vector E, times the vector E, plus epsilon times the divergence of the vector E, times the vector E, plus epsilon times the directional derivative of the vector E in the direction of itself. The later can be expressed by epsilon times the gradient of 1 over 2 times E squared in the case of an electrostatic field which is curl-free, as it was shown when we derived the explicit form of the stress tensor. At the same time, we also split the last term in the right-hand side into negative 1 over 2 times E squared times the gradient of epsilon, and negative 1 over 2 times epsilon times the gradient of E squared. The third and the last terms in the right-hand side cancel out each other, reducing the right-hand side of the equation to 3 terms. Now we apply the first Maxwell equation in electrostatics, stating that the divergence of the product of the absolute permittivity epsilon and the field strength E at any point of a polarized dielectric medium is equal to the volume density ρF of the free charges at that point. This equation can be written in the form stating that the dot product of the vector E times the gradient of epsilon, plus epsilon times the divergence of the vector E, is equal to the free charge density ρF. If we express epsilon times the divergence of E by ρF minus the dot product of E and the gradient of epsilon, then we can substitute it into the second term in the right-hand side of the force density formula, which gives us 4 terms. Because the first and the third terms cancel each other out, we conclude that the force density F produced by an electrostatic field E in a charged and homogeneous dielectric medium of absolute permittivity epsilon is equal to the difference between the volume density ρF of free charges in the medium times the field strength E, and 1 over 2 times the square of the magnitude of the field strength E times the gradient of the absolute permittivity epsilon of the insulating material. However, this is not the most general formula for the electrostatic force density acting on charged dielectric materials placed in an electrostatic field. We can assume that the dielectric medium is homogeneous, but it can still be the case for liquid dielectrics that its permittivity depends on the density ρ of the fluid. We note that the absolute permittivity of a fluid can be a function of its temperature as well, which makes its behavior even more complicated in electrostatic fields. As a result, a liquid dielectric of a fixed mass m given by the product of its density ρ and its volume v, any modification in the density or temperature causes a change in its electrostatic properties. For example, if we perform a quasi-static infinitesimal isothermal compression on the liquid, the compression changes both its density and volume. Then we can determine the variation of these quantities, stating that the vanishing variation of the fixed mass m is equal to the infinitesimal change d ρ in the density times the volume v, plus the density ρ times the infinitesimal change dv in the volume. Hence, the differential of ρ can be written as negative ρ times the differential of v over v. We already established that the energy density U of an electric field E in a dielectric medium is given by 1/2 times the absolute permittivity epsilon of the dielectric, times the square of the magnitude of the field strength E. If we keep the electric field fixed during the isothermal compression of the dielectric fluid, we can write the differential du of the energy density as 1/2 times E squared, times the differential of its absolute permittivity epsilon. Since the compression of the liquid is performed at a constant temperature, the differential of the permittivity is given by the partial derivative of the permittivity epsilon of the fluid with respect to the density ρ of the liquid at a constant temperature T, times the differential of the density ρ. The latter can be expressed in terms of the differential of the volume of the liquid, and we obtain an equation stating that the differential of the energy density U is equal to -1/2 times E squared, times the partial derivative of epsilon with respect to ρ at constant T, times ρ times dV/V. At the same time, the energy U of the electric field at a volume V of the dielectric medium is given by the energy density U as a function of the volume V of the liquid, times the volume V. Then the variation of the energy U of the electric field under the isothermal compression of the dielectric fluid can be written as the volume V of the liquid times the differential of the energy density U of the field, plus the energy density U times the differential of the volume V. If we insert the expression obtained for the differential of the energy density and the explicit form of the energy density into the right-hand side, we can write the differential of the energy U as 1/2 times the difference between epsilon and ρ times the partial derivative of epsilon with respect to ρ at constant T, times E squared times dV. In the case of the isothermal compression of the dielectric fluid at a constant field strength E, the pressure P of the liquid is given by the negative partial derivative of the energy U of the field stored in the fluid with respect to the volume V of the fluid, while the temperature T and the field strength E are kept constant. Then the derivative of the formula obtained for dU with respect to the volume V gives two terms for pressure. The first term is equal to 1/2 times epsilon times E squared, which is the Maxwell stress contribution already included in the stress tensor. The second term, however, represents a pressure correction that arises naturally from the dependence of the dielectric constant on density. This gives the Korteweg-Helmholtz force density describing the force acting per unit volume in a dielectric medium of absolute permittivity epsilon and density ρ due to an electrostatic field E, where the free charges in the medium are given by the volume charge density ρf. As the formula shows, the force density F is equal to the volume density ρf of free charges times the field strength E, minus 1/2 times the square of the magnitude of the field strength E, times the gradient of the absolute permittivity epsilon, plus the negative gradient of the correction pressure given by 1/2 times the density ρ times the partial derivative of the absolute permittivity epsilon with respect to the density ρ, times the square of the magnitude of the field strength E. Although this equation is the combination of the two results derived for inhomogeneous dielectrics and homogeneous dielectrics with density-dependent permittivity, it still holds true for the general case with inhomogeneous dielectric media with density-dependent permittivity.